Welcome back everyone to section number 2. This is a section about the mean value theorem, and we're talking here about a strange consequence about the mean value theorem. And this is going to be a short video, but the claim is this is an important concept that will come back later in this chapter at the very end, and then again in chapter number 4 as well. So we're going to try to understand this interesting result of the mean value theorem, and then we're going to try to solve a few problems related to this idea. So the consequence of the mean value theorem that we can prove using, again, the mean value theorem. This is a corollary. This is a result from the mean value theorem. It says if the derivative is equal to 0 for all x in some open interval here, a, b, then on this interval the function must be constant. So f of x must be constant on that interval. Okay, and that kind of makes sense, right? Because usually we would think about this maybe going in the opposite direction, that if you have a function that's a nice constant, if you have some c value here, and let's suppose that our function is some constant, c, then when you take the derivative of it, f prime of x, well, the derivative of any constant is 0, right? We have nice horizontal tangent lines, or again, the slope is 0 at any one of these points. And so you almost ask yourself, right, what is this corollary even telling you, right? And so this is actually almost in reverse here. This is if you have a function that's a constant, then its derivative is 0. This is going the other way, right? If your derivative is 0, then your function must be a constant. So you do have to be careful about, those sort of statements back in the maybe good old geometry days, right? All squares are rectangles, but not all rectangles are squares, right? Sometimes you can only go in one direction. This is saying that you can actually go in both directions, that if your derivative is 0, it must have come from a constant. And so again, you can actually prove this using the mean value theorem. And so this last remark here is, why does it matter? And the claim is that in our calculus class, right, we deal with relatively nice functions, right? We deal with relatively nice functions, but there are really horrible functions out there. And so can you be so creative maybe with how you're defining your function? Maybe if you made it super piecewise or something like this, could you be really creative and make some function where the derivative is 0 and yet it wasn't constant, right? Maybe if you did something where you did like a bunch of dots and they jumped up and down and stuff like this, so it almost started to look like two straight lines sort of deal. Maybe you could do something really creative and make something that has the derivative 0 and yet it's not constant. And the claim is, this is saying, no, you can't do this. No matter how creative you are, no matter how horrible your functions are, the only ones that have derivative 0 are constants. All right, so I decided to jot down some words here. And again, the reason why does it matter is because there are some really horrible functions out there. And mathematicians, right, we're always wondering if something is true most of the time or all of the time, right? And we really hope that it's true all of the time, and then it becomes like a theorem or something like this. So in this case, it is true all of the time, right? The only way that you can get something with a derivative being equal to 0 on some interval is for that function to have been constant. And now we can actually upgrade this as well. So if two functions have the same derivative, so if f prime of x is equal to g prime of x, this is actually related to this previous one up here. The claim is the only way that two functions can have the same derivative is if they're off by a constant, right? So if they're off by a constant, that's okay, because again, that constant will have derivative 0. Okay, so I would like to actually get a little bit of practice applying this right here, and you'll see some on your homework problems, and then again later on, because this does get used later on. So I'd like to find a function f of x where its derivative is equal to 2x. So, okay, let's go ahead and think for a little while. Something that we know that has a derivative of 2x. So, okay, in this case, maybe you could do f of x is equal to x squared. So this is a little bit of a guess and check sort of deal, right? So if I guess x squared, then its derivative here is going to be equal to 2x. Okay, so yes, this one works out. This is a nice fine function whose derivative is 2x. In part B, find a different function, f of x, that satisfies the derivative is equal to 2x. right? And so this up here says, well, if you want them to have the same derivative, and yet this being a different function, the only way you can do this is if it's off by a constant, right? No matter how creative you are, no matter how horrible your function is, the only way that you're going to achieve this is that if it's essentially the same thing as up here and then off by a constant. So I'm going to do f of x is equal to x squared plus 47, right? Any constant right here works. You can do plus pi or plus e, or plus the square root of 2 or plus 1 or something like this, right? So this is a different function than it was before. Now there's this plus 47, but now notice if you take the derivative of it, f prime of x is equal to 2x plus 0. So again, like I said, that this is actually related to the previous one, because again, the only thing that has derivative 0 are constants. So that's essentially what we're using in this one right here. So here's two different functions, both of them having the derivative of 2x. All right, that's it for this video, and that's it for this section. I'll see you guys next time in section 3.